Alright, for 29, it's asking you whether you can use the rational root theorem and synthetic division to factor this polynomial. And again, this is going to cause a problem because it's an irrational number, because the p's and the q's are both plus or minus 1 and plus or minus 5, right? So then when you, these are the p numbers and the q numbers. So when you do p over q, you have plus or minus 1 over 1, plus or minus 1 over 5, and then 5 over 1, and 5 over 5 is already on the list, it's 1. So this is the list of possible rational zeros for this polynomial, and when you multiply and you use synthetic division, it's not going to work, because you cannot get an irrational number, an irrational number from a rational number. Okay, so number 30, what does the rational root theorem find? It finds rational roots or zeros of a polynomial. Alright, so for 31, they ask you to list the steps or describe the process of finding rational zeros of a polynomial with integer coefficients. So first you find the factors, the p factors, which are factors of the constant, then the q factors, which are factors of the leading coefficient. Make your list of p over q numbers, and then use those p over q numbers in synthetic division. The ones that have a remainder equals 0 are the roots. Those are the ones you're looking for. And that's it. Alright, so for number 32, we get plus or minus 1, 2, 3, 4, 5, 6, 10, 12, let's see, for 15, 20, 30, and 60. So these are all possible rational roots of this polynomial. Now the good thing is that q is plus or minus 1. These are all p-values. So your p over q is going to be basically this list right here, because you're going to put them all over 1, so it's going to stay the same. So now we're going to use synthetic division to find the roots, the zeros. Alright, since we don't know how many of these numbers we have to go through, and there's a lot, I'm going to go ahead and use synthetic division, set it up this way like I showed you in class the other day. Instead of doing them individual, we're going to just make one table with all the synthetic divisions in one table. So you bring down the 1 from the top, and then you do 1 times 1 is 1, but in your head you add 1 plus 2, okay? And you put that answer right here. Then 3 times 1, and again it's this 3 times this 1. So 3 times 1 is 3, and then again in your head you subtract 23 from it, so that gives you negative 20. Then negative 20 times 1 is negative 20. You're going to add in your head, you're going to combine it with negative 60, so that's going to be negative 80, so no way. Let's try negative 1. Bring down the 1. 1 times negative 1 is negative 1, plus 2, because again you're always working with the numbers up here on the top. Okay, so negative 1 plus 2 is 1. 1 times negative 1 is negative 1, minus 23 is negative 24, and negative 24 minus 60 is negative 36, which is still not good. 2. Bring down the 1. 2 times 1 is 2. 2 plus 2 is 4. 4 times 2 is 8. Negative 23 plus 8 is negative 15. Negative 30 gives you negative 90. Okay, not good. Negative 2. I'll bring down the 1. 1 times negative 2 is negative 2. Negative 2 plus 2 is 0. 0 times negative 2 is 0. 0 minus 23 is negative 23. And then that gives you 46. 46 is negative 16. So notice how the negative numbers are getting closer to 0, while, watch, the positive numbers like 1 and 2, it's getting further away from 0. Whereas the negative numbers, negative 1 and negative 2, are getting closer to 0. So I'm going to skip 3 and go to negative 3 and see if that pattern continues. So I'm going to skip over and do negative 3. So 1 times negative 3 is negative 3, plus 2 is negative 1. Negative 1 times negative 3 is 3. 3 minus 23 is negative 20. And then negative 3 times negative 20 is 60. 60 minus 60, and it worked. So this is a root. Now, these three numbers represent x squared minus x minus 20, which factors of negative 20, negative 5, and 4, that add up to negative 1. So my complete factorization of that polynomial is going to be f of x equals x plus 3 times x plus, minus 5, minus 5 times x plus 4.